Okie doke. About that time? Well, good afternoon, everybody. Hope everybody's doing well this afternoon, or as well as you can do under the circumstances. Hope everybody's finding stuff to do. Well, again, I'm sorry this happened. I wish it hadn't happened, and we're just going to do the best we can to make things right now. So, most important thing to talk about is that Stats Quiz 2 is Friday. Okay, Friday, March 27th is Stats Quiz 2. And I've got it. It's in the quizzes section of the Canvas site. And all this information is in an announcement on the Canvas site as well. But let me just reinforce it verbally here. So at midnight on Friday, essentially 12:01 a.m. on Friday, the test will become live. It's open book, open notes, and there's no time limit on it. But you're not allowed to use another classmate or use another person. So that would be cheating if you use somebody else. So you're expected to do it on your own. So what you'll see when you get to the quizzes section, there'll be a link for stats quiz number 2. And you'll get 2 stats problems. One will be an ANOVA, one of these 3 problems down here. Between subjects one-way ANOVA, within subjects one-way ANOVA, or between subjects factorial ANOVA. And one of the problems will be an old problem, a test of a single sample mean, between subjects t-test, within subjects t-test, or between subjects variance test. Now, I wish there were an easier way to do this, but you're going to have to do the problems on your own paper. What you're going to put into the computer is you're just going to type in the name. There'll be a text box there. You just type in the name of the test that's appropriate. That's all you do on the computer. And then what you need to do is that work both problems on your own paper. And then when you're done, you got 2 options. You can take a picture of them and then email it to me. And I'll put my email address up there. So, yeah, this is Psych 301 Research, Design, and Methodology. And my email address is ecooper@iastate.edu. So you can just take a picture of your work, make sure that it's legible, that you can read all of it before you send it to me. And then you can just email it to my email address, and I'll grade it. Or if you don't have the ability to do that, and I understand you might be in that situation, then what you can do is just mail your work to me. And the mailing address is Eric Cooper, W112, Lago Marcino Hall, Ames, Iowa, 50010. Okay, or you can mail it to me there. Now, I guess the only time limit is that the test is going to disappear at 11:59 p.m. on Tuesday, and that would be, let's see, 27, 28, 29, 30, the 31st. Okay, Tuesday the 31st at 11:59 p.m. the test is going to go away. And so you have to have completed it by then. If you're going to mail in your test, the postmark has to be by Wednesday, April 1st. Must say Wednesday, April 1st or before for me to accept it, okay? I'm sorry we have to do it this way. I apologize. I just don't see any other way to do it, okay? So if you got questions before the stats quiz, my email address is right there, and so you should feel free to ask those questions. Okay, well, let's get on to the main task today. I'm going to go a little bit out of order on the syllabus because we're supposed to start correlation today. I still have not figured out how to do stats problems, but I'll try and work on that this weekend. So I'm going to skip down in the syllabus, and the topic we're going to talk about now is single subject designs. And single subject designs are often called N=1 designs. That's what we're going to talk about today. All right, so what do I mean by this? Well, single subject designs, the definition is designs based on testing one subject. One subject. That is, for all the other research techniques we've talked about in here, we have used more than one subject. So we've done group research. There are some people who do single subject designs, and particularly HDFS, Human Development and Family Studies, is a department that uses a lot of single subject designs. And then also, I would say school psychology is another field that uses a lot of single subject designs. Now, in general, there are two types of single subject designs, and let's list what those are. First are case studies, and then the second type are experimental single subject designs. Okay, and so let's talk about each of these because they're rather different. So let's begin by talking about what a case study is. A case study is a description of the behavior or abilities of a single, usually exceptional individual. Case study. Let me move that up. Sorry. Case study, a description of the behavior or abilities of a single, usually exceptional individual. So what I mean by that is you've got somebody who is out of the ordinary for one reason or another. Maybe it's they're extraordinarily good at something, or maybe it's because they've got brain damage and they're very bad at something. But either way, they're different than the average person. And what you're doing in a case study is kind of documenting how they are different from the average person. So a lot of you may be familiar with Freud and how he developed his ideas for psychoanalysis. It was based on a case study of one of his patients, Anna O., and that served as the basis for most of his ideas. And there have been a number of case studies very famous within psychology. But a lot of you are familiar with H.M. We talk about him in Psych 101. H.M. was a patient. He just died a few years ago. He had very, very severe epilepsy, and as a result of that, they tried an experimental surgery on him because his epilepsy was life-threatening. They tried this experimental surgery that they thought would cure it, and so, like most epileptics, HM had some damage to his temporal lobe that occurred prenatally, and typically what you want to do is take the damaged tissue out of the temporal lobe. Well, they did take the damaged tissue out, and he did his seizures from his epilepsy stopped as a result of that. But what they didn't realize is that they also took out his hippocampus, and that was a very bad thing to do, because the hippocampus is a structure that's responsible for transferring information from short-term to long-term memory. If you don't have a hippocampus, what it means is you can't learn anything new. So HM, for the rest of his life, after he had the surgery, only had short-term memory. He wasn't able to transfer anything. Well, that's not right. He wasn't able to transfer anything from short-term to long-term memory. He still had his long-term memories that he already had prior to the operation, but he wasn't able to create any new ones. So after the operation, he went home, and he was still able to find his way around his house because he knew the layout from before the operation. But later, he and his mom moved to a new house, and in the new house, he didn't know the layout, and so every day for the rest of his life, when he wanted to go to the bathroom, he'd have to ask for directions. He'd get up and look out at his lawn to see if it needed to be mowed several times every day, even in the winter. He had a huge stack of magazines next to his bed that he just kept reading over and over and over again because, he couldn't remember them. Now, he was in his early 20s when he got this surgery, and so, he didn't realize, of course, he thought he was still in his early 20s because he couldn't transfer anything to long-term memory even after the surgery. And so one of the most, worst aspects of it, I guess, is he'd go to the bathroom or look in a mirror and expect to see a 23-year-old face looking back at him, and he sees a 60 or 70-year-old face looking back at him, and it sort of freaked him out. So they try and keep him away from mirrors as much as they possibly could. Well, he was studied for years and years. He was essentially a professional research subject, both at MIT and then later at McGill University. And there have been dozens of studies done on, dozens, probably hundreds of studies done on HM to tell us about the distinction between short-term and long-term memory. That's very useful. A lot of what we know about short-term memory comes from the experiments that were done with HM. Now, another one, I do a lot of case studies myself. I studied, one guy I studied was Rajan, the memory guy, and I don't know if you've heard about Rajan, the memory guy, or not. He is famous. At one time, he held the record for memorizing pi. You know, pi, it's an irrational number that goes on forever, 3.14159.265. That's as far as I know it. And so that's a way they test these guys with great memories. He had memorized pi to 40,000 digits at one point. If you ask him how he did it, he says he has a trick. He says, well, what I did is I broke it down into blocks of 5,000. I guess that makes it really easy if you do it that way. So anyway, Rajan, the memory guy, was famous for doing this. I don't think he's in the Guinness Book of World Records anymore. But what he's famous for is that he has incredible memory, but it's only for numbers. It doesn't extend to anything else. So he used to be he was a graduate student at K-State, and what they would do to test him there, actually in the psychology department, what they would do to test him there was they'd give him these huge matrices of numbers, so like this big sheet of paper that had like 100 columns of numbers and 100 rows of numbers, so 10,000 numbers on the sheet. They'd have him take that home for the weekend and then come back on Monday, and then they'd ask him, all right, what number is in row 73, column 62? And he'd be able to tell them after just studying the 10,000 numbers over the weekend. Well, I did some tests on him when I was in graduate school. I was in graduate school at the University of Minnesota. He'd visit Minneapolis now and then, and when he would visit the psychology department, and we decided to do some tests on him. What I looked for was his memory for pictures. So I had him name 32 pictures that popped up on a computer screen. So they'd come up one at a time, and half of them would be on the left side of the screen and half would be on the right side. And then of those, half would be pointing to the left, and the objects would be pointing to the right. So the first time I just had him go through one at a time and name the objects. And then I went through all the objects a second time in a different order. And some of the objects were on the opposite side of the screen that they had been the first time. And then and some were on the same side. And then half the objects were pointing the same way they had been the first time, and half were pointing in the opposite direction. And so all he had to say was, are they pointing the same way? Are they pointing a different way? Are they on the same side of the screen, or are they on a different side of the screen? So I wanted to see how well he remembered the orientation and the location of the pictures. Now I used, because he was a graduate student in psychology at K-State, I used graduate students in psychology at the University of Minnesota as the control group. And he did differ reliably from the control group in his memory for the pictures. He was reliably worse than the control group, interestingly. So he has super, super great memory. He does things with numbers that I think most of us can't even imagine, but his memory doesn't extend to anything else at all. The other case studies I do a lot is I have a prosopagnosic patient, and prosopagnosia is a condition where somebody usually has had a stroke, and as a result they can't recognize people's faces anymore, so they couldn't tell, like she can't tell me from my graduate students when I go to visit her by looking at our faces. But you can identify other objects like tables and chairs and things like that. And so I do tests on her usually once a year. We just went out this year over Martin Luther King Day to do some tests on her. And so I have a theory about how face recognition and object recognition differ, and actually she helps me to test my theory. There are certain tasks I predict she should be able to do, and some tasks that she shouldn't be able to do if my theory is right. And so I go out and test her. So I think case studies can be very useful, and they've been very famous in the history of psychology. Problem is you don't have a lot of control over the situation. I'm only testing my one patient, of course, and she has kind of unique brain damage that's unique to her. So if she can't do a particular task, do I know that that is going to be true of all prosopagnosics? Because she has some parts of her brain that have been damaged in common with all prosopagnosics, but like pretty much all brain damaged subjects, she has, a unique pattern of damage. So other parts of her brain were damaged too that aren't damaged in most prosopagnosics. And so if I find a deficit in her, it's quite possible it's one of these other areas that's not really involved in prosopagnosia that's responsible for the deficit. So that's the problem with drawing an inference based on one subject. You don't know what else might be going on that could actually also explain your data. So what I'm going to say is case studies are a lot like naturalistic observation. Case studies are best used to generate hypotheses later testable by other methods. Okay, case studies are best used to generate hypotheses later testable by other methods. That's what I would say about that. Okay, well that's it for case studies. Now, let's go on to talk about the next type of single subject design. And these are experimental single subject designs. These are designs in which the effect of an IV on a DV is examined using one subject. Designs in which the effect of an IV on a DV is examined using one subject. So what you're trying to do is you're trying to do an experiment, but so you're manipulating an independent variable of some sort, but you only have one subject when you're doing this research. So let's think about maybe some of the problems with this. This sort of research is done, like I said, in school psychology. School psychologists are often working with kids who have some sort of behavioral problem, like they might work with an autistic kid who's maybe hitting himself all the time, and you want to stop him from hitting himself. It's not good for them to do that. And so, let's say you have some sort of intervention. You're going to give him like a piece of candy for every 10 minutes he can manage not to hit himself, and then measure his behavior before that treatment and after the treatment. And so we can measure his number of hits the week before treatment, and we can measure his hits after. I'm not putting that in. Stop that. Okay. So let's say, I don't know, before our treatment, he was hitting himself 56 times a week. And after the treatment, he's only hitting himself 49 times a week, for example. Okay. Now, this is kind of weird. This is a one subject, so this is a within subjects design, right? Our two conditions, our IV levels, are before treatment and after treatment. If you remember, so it's a within subjects design with one subject, right? This is the kind of weird thing. And so we got two IV levels. It's a within subjects design. I want to compare the means of my two IV levels. I know it seems a little weird to talk about the mean of one score, right? But remember the definition of what a mean is. It's the sum of x, the sum of all the scores, divided by the number of scores. And so we could add up this score, which is just 1, and it would be 56, and divide by the number of scores, which is 1. So the mean is 56 here, and the mean is 49 here, right? If you only have one score, then the score itself is just the mean. And so if you remember, so we're comparing the means, we got two levels, and so within subjects design, so that's the within subjects t-test, right? That's the appropriate stats analysis would be the within subjects t-test for this. So if you remember, we have to calculate the difference scores in the within subjects t-test. So we'll take the before minus the after. The difference score is going to be 7 then, 7. Now, if you remember the degrees of freedom on this test, if you're doing the within subjects t-test, is the number of difference scores minus 1 equals your degrees of freedom. But in this case, we got one different score, right? The 7, it's the only one. So 1 minus 1 equals 0 degrees of freedom for this test. All right. Well, let's go get our t-table. I'm going to look up the critical value with 0 degrees of freedom. Here's my t-table. I go to the degrees of freedom column and there's no 0. It starts at 1. That's right. It starts at 1. You have to have at least 2 different scores before you can do the within subjects t-test. And now you see the problem here. Now you see the problem. The problem is one cannot perform statistical tests. Yeah, statistical tests on single subject designs. One can't perform statistical tests on single subject designs because they only have 1 degree of freedom. You don't know how much variance there is in the dependent variable is the real problem. So what do you do? Well, in single subject designs, whether or not a treatment is effective is determined by simply inspecting the data. Yeah, simply inspecting the data, meaning you look at the data and see, yeah, it looks like it's having an effect, or no, it doesn't look like it's having an effect. That's what it amounts to here. So let's go back to our design here. We can't do statistics on it. Well, he was hitting himself 56 times before the treatment and 49 times after the treatment here. And so he was hitting himself less after the treatment than before. That's what we wanted. So do we conclude that the treatment was effective? Well, you maybe can see a problem here. If you measure something twice, like whatever, whether how much the kid hits himself, or if we went out twice during the day at random times and measured the temperature or measured anything twice, what's the odds that the second measurement is higher than the first? Well, it's the same as the odds that the first measurement is higher than the second, so 50% chance, right? 50% of the time the first measurement's going to be higher, and 50% of the time the second measurement's going to be higher, even if your independent variable isn't having any effect whatsoever, right? So essentially, if you do a design where all you're going to do is, well, I measure the kid before we give him the treatment and measure him afterwards, and then I'll say my treatment is effective if he hits himself less the second time I measure him than the first, well, you have essentially a 50% chance of making a type 1 error, and that's ridiculously high, of course. So we don't want our type 1 errors to be that high. And so that's why the people who do these sorts of designs, they don't do it this way where they just measure somebody once before treatment and once afterwards. They have ways to try and get around this problem that you can't inspect. Data can't be has to be inspected to determine whether the independent variable is effective in a single subject design. So what we're going to talk about now is we're going to talk about the types of single subject experimental designs. Let's spell things right. Designs. Okay, types of single subject experimental designs. Now, there are going to be 3 of these experimental single subject designs we're going to talk about. And it's just like when we talked about the quasi-experiments. Remember the quasi-experiments we talked about in the lecture right before spring break? We talked about the single group pretest post-test design, the interrupted time series design, the non-equivalent before-after design, and the ex post facto design. The questions on midterm number 2 about these are going to describe how somebody did their research, and then you have to say which design they were using. We talked about the 4 quasi-experiments, but that's the way it's going to be with these single subject experimental designs as well. So as I go through these designs, what you need to keep in mind is, could I identify this sort of design from a description? And I'll try and give you, just like I did with the quasi-experiments, I'll try and give you specific things to look for that'll help you to identify these designs. Okay, so the first one I want to talk about is the reversal design, and it's sometimes called the ABAB design. You can use either term that you'd like. In reversal design, behavior is observed. Behavior is measured prior to any treatment. This is the A phase. Then a treatment is introduced and behavior is measured again. This is the B phase. Then the treatment is withdrawn and behavior is measured again. It's the A phase again, where the subject is not under the treatment. And then the treatment is reintroduced and behavior is measured again. And that would be the B phase again when you measure them under the treatment. Okay, so the idea of the reversal design, or the ABAB design, is we're going to measure the subject when they're not under the treatment and when they're under the treatment. And if the treatment is the thing that's causing the reduction, well, then when we remove the treatment, behavior should reverse to where it was before. That's the idea, is if the treatment was causing the change in behavior, after you remove the treatment, the behavior should reverse. That's where the reversal design comes from. So let's say we had a kid that was hitting himself, an autistic kid, and we have a program that we think will help the kid out. And so during the A phase of the program, he had 67 hits, let's say. So this is before we've given him any treatment. Then we introduce our treatment. That's the B phase. And now he goes down to 23 hits the week we're doing the B phase. All right, now we're going to remove the treatment and see if behavior reverses to where it was before. So we'd expect it to go back up again. Let's say it goes up to like 62 hits after we remove the treatment. And now we're going to have the B phase again, where we're going to reintroduce the treatment. If the treatment's working, it should go down, let's say 32 hits this time. So it looks like now the A phase, he's hitting himself a lot, and the B phase, he's not hitting himself so much. The B phase is when he's under our treatment. So we're going to conclude the treatment is effective because the two B phase dependent variables were lower than the two A phase. That's the idea. So you're not just measuring the person once. That would be once before and once after. That would be like the top two here. You're going to do it again to make sure it comes out again. All right, so the idea is that you're going to conclude the treatment is effective if these two, the B phase, are both lower than these two, the A phase. That is when you conclude that the treatment works. Now, there are some problems with this. Problems still, you got one. First, placebo effects. Your subject is definitely going to know when they're under the treatment and when they aren't, usually. And so they may have just gotten better because they expect to get better. And there's also a still... I'm sorry. I got to move this up. I'm sorry. So problems is problems with the reversal design. Placebo effects is one. The subject is getting a treatment, and so they might get better just because they expect to get better. Second is still a good likelihood of type 1 errors. Still a good likelihood of type 1 errors. What I mean by that is, remember, if we measured it once and then measured it again, we got a 50% chance of making a type 1 error there. Here, remember, we're going to say the treatment's effective only if the two B phases are lower than the two A phases. There's still a 17% chance of that happening, even if the treatment is not effective at all. And so that's still a 17% chance of making a type 1 error, which most people consider too high. And third is only works for treatments that are temporarily effective. All right, this is kind of a weird one. Remember, the whole idea of the design is when you remove the treatment, the behavior has to reverse to where it was before. At least it has to get worse. And you're not going to conclude the treatment works unless that happens. And so what if you had a really, really good treatment that when you gave the kid the treatment, it like permanently fixed him? And so now, let's say now the A phase, instead of 62, now it's like 31 or something, so it's still really low because you permanently fixed the kid with your treatment. Well, you're going to conclude, oh, my treatment doesn't work because this A phase is lower than this B phase here. So, gosh, I guess my treatment is no good. Well, no, your treatment is actually really, really, really good. The problem is you can only test things in this design there where the treatment doesn't work anymore after it's not being applied because you can't see the reversal otherwise. So that's kind of a weird thing about this one. You're only going to conclude that a treatment's effective if it's not very effective. In other words, if it doesn't permanently solve the problem. All right, well, let's look for things to look for in the reversal design. So, again, of course, it's a single subject design, so it has to be one subject that's being tested for it to be the reversal design. So I would say the thing that makes it unique is it has one treatment for one behavior. None of the others are like that. So one treatment for one behavior is a unique thing about the reversal design. And then you're going to measure the subject without the treatment, give the treatment and measure the subject again, withdraw the treatment to see if behavior reverses and measure the subject again, and then you're going to give the remove the treatment, give the treatment again and see if it works again. So one treatment for one behavior, that's the reversal design. All right, now we're going to talk about the next single subject experimental design, and that is the multiple baseline design. Multiple baseline design. All right, multiple baseline design is kind of complicated, so what I'm going to do is I'm going to list the steps here. I'm just going to write them down, and then after I've written them down, I'll go through an example, okay? So step one when you're doing the multiple baseline design is that several different behaviors of one subject are monitored. Okay, several different behaviors of one subject are monitored. So you got several different dependent variables. B, a treatment is applied to only one of the behaviors you're measuring. C, the researcher determines if the treated behavior changes relative to the others, the ones that aren't being treated. And D, the process is repeated for each of the other behaviors. The process is repeated for each of the other behaviors. Okay, so here's the idea of a multiple baseline design. Let's say we've got a kid who's having behavioral problems in class. We'd like to get an intervention or maybe several interventions to try and improve the kid's behavior. So we're going to have three dependent variables, three aspects of his behavior that we are measuring. We're going to measure, let us say, how many times he gets up from his seat. We're going to measure how much time he spends bothering other kids. And we're going to measure how much noise he makes. Those are our three measures. How many times he gets up from his seat, how much time he spends bothering other kids, and how much noise he makes. So we'll measure them all for a week. And then we'll introduce a treatment for one of those behaviors. Like, we'll give him a piece of candy for every 5 minutes he can stay in his seat. So I'm going to try and get him to stay in his seat, and we'll give him a piece of candy for that. And we'll do that for a week. And then what we're going to do is we're still measuring all three behaviors. The idea is we're going to use the other behaviors we're not treating as a control condition for the one we are. The idea is that the kid's behavior is going to fluctuate over time. Some weeks he's going to be worse than others. And so we can use the two behaviors we're not treating as a control condition for the one we are treating. So the idea is if he stays in his seat more, if that behavior improves, but he's still bothering the other kids and making as much noise as before, or at least there's a change in the variable that we've treated relative to the other two, well, then we're going to conclude that our treatment worked for that. Okay, well, now we're going to try and treat him for the amount of noise he makes. So we'll give him a piece of candy for every 10 minutes he can not make noise. And so we'll see if that behavior goes down relative to the other two. We'll do that for a week. And then we'll do the third behavior. We'll give him a piece of candy for every 10 minutes he can spend not bothering other kids, and see if that behavior goes down relative to the other two. So the idea is if each treatment, and spell it right, if each treatment is effective, then the behavior that is being treated should go down relative to the behaviors that are not being treated. Sorry, let me move that up. If each treatment is effective, then the behavior that is being treated should go down relative to the behaviors that are not being treated. And that's when we're going to say a treatment is effective. All right, well, you might see a problem with this. Let's think about this. We're going to give a kid a piece of candy the first week for, well, I guess the second week. The second week, after we've already measured them all the first week and weren't treating anything, in the second week, we're going to treat him for getting up out of his seat. And we're only going to conclude that our treatment for keeping him in his seat works if that behavior goes down relative to the amount of noise he makes, the amount of time he spends bothering other kids. Well, the problem with this is that these treatments the dependent variables aren't independent of one another. And so a treatment that's effective for getting him to stay in his seat would almost certainly reduce the amount of time he's spending bothering other kids as well. And if it affects that behavior as well, again, we're not going to conclude that our treatment was effective because the behavior we were treating didn't go down relative to the others. The other behaviors went down as well. So we aren't going to conclude that. So the problem with this one, and it's a big one, such a big problem that I think it almost precludes using this in most cases. Problem, in order for the logic of the design to work, the behaviors being measured must be completely independent of one another. In order for the logic of the design to work, the behaviors being measured must be completely independent of one another, meaning if I affect one, then that doesn't affect any of the others. And that's almost never going to be the case. If you got three behaviors that are measuring essentially the same thing, in this case how bad the kid is, if you affect one, it's almost always going to affect the others. Okay, well, let's talk about, for this is the multiple baseline design, things to look for. Multiple behaviors are measured with one treatment for each. Multiple behaviors are measured with one treatment for each. So that's the unique thing about the multiple baseline design. It's the only one with multiple dependent variables, multiple behaviors that we are measuring. That's how the way I remember that is multiple baseline has multiple behaviors. Multiple baseline has multiple behaviors. If you can remember that little phrase, that will help you to identify the multiple baseline design. Again, of course, it has to be a single subject design, like the reversal design does. Okay, well, that's the multiple baseline design. Again, if you had any questions about that, you should email me at ecooper@iastate.edu. Let's talk about the third design you need to know, and this is the multi-element design. This is the third single subject experimental design that you need to know. Okay, the multi-element design is, well, sort of like the reversal design. Say, during each time period during the research, one treatment is introduced for one behavior, and the behavior is measured. This process is repeated multiple times for each treatment that is being tested. After testing, I'm sorry, keep going low. I'm sorry. Let me move it up here and let me go slow over it again. I'm very sorry. Multi-element design. During each time period during the research, one treatment is introduced for one behavior, and the behavior is measured. The process is repeated multiple times for each treatment that is being tested. After testing, the average of the dependent variable is computed for each treatment, and the treatment with the best average effects is deemed best. Okay. During each time period during the research, one treatment is introduced for one behavior, and the behavior is measured. I guess that should have a comma. Okay. This process is repeated multiple times for each treatment that is being tested. After testing, the average of the dependent variables computed for each treatment, and the treatment with the best average effects is deemed best. Okay, you use the multi-element design when you've got several different ideas for how you might affect one behavior. So let's say we've got a dog that's destroying our furniture. We have some ideas we think will get the dog to stop destroying this furniture, and we want to see which of the ideas we have is best. So we're going to randomly select one of the three treatments that we've decided on. Let's say, well, I don't know, pet the dog for every 10 minutes it can't destroy the furniture. That might be the first treatment. And for a week we're going to do that. We'll measure how much furniture destruction the dog does during that week. Then the next week we'll try our another idea. So we might give the dog a treat for every 10 minutes that it doesn't destroy the furniture. We'll measure how much furniture destruction the dog does that week. Then the third week we introduce a different one. We'll slap the dog on the nose every time it destroys the furniture, measure how much furniture destruction it does that week. Then typically what you do is start the process over again. Then you're going to do a fourth week where you're going to randomly select one of the treatments, and you're going to keep doing this. The more times you do it, the more times you try each treatment, the more confident you can be about the results when you're done. Well, after you've done this several times, let's say you've tried every treatment for 5 weeks, what you're going to do is average how much furniture destruction the dog did under treatment 1, how much under treatment 2, and how much under treatment 3. And whichever treatment has the least furniture destruction, you're going to say, okay, that's the best treatment. So this one is used when you have several different treatments for one behavior and you want to find out which treatment is best. Okay, well, the problems with this one are essentially, I think, very similar to the ones with the reversal design. Only works for treatments whose effects do not persist when withdrawn. It only works for treatments whose effects do not persist when withdrawn. So you got this problem that you're giving multiple treatments to the same dog, and you've got a problem with carryover effects. Maybe the effects of one treatment bleed into the next week and are affecting the dependent variable for the next treatment. You don't really know, and so the effects of one treatment may persist when another treatment is introduced. Okay, well, I'd say the things to look for the multi-element design, things to look for are several treatments for one behavior. Several treatments for one, and let's spell behavior right. Behavior, okay, several treatments for one behavior. So this one is when there's one behavior you're studying, one dependent variable like furniture destruction, and then you got several different treatments you think might improve that situation, and you're trying to find out which one is best. So let's summarize the things to look for. In the reversal design, that's when you measure the subject, give the subject a treatment and measure them again, withdraw the treatment and measure them again, give the subject the treatment and measure them again. So you got one treatment for one behavior in the reversal design. Multiple baseline design, you got several different behaviors you're measuring. It's really the only design in the whole class where you got multiple dependent variables. And then you've got one treatment for each. So multiple baseline has multiple behaviors. And then multi-element design, that's when you got one behavior you're treating, one dependent variable, and then several different treatments, and you want to figure out which treatment is best. That's the multi-element design. I would say the most common mistake I see people make is they'll put the multiple baseline design down when it's actually the multi-element design. So be careful about that. Okay, now let's talk a little bit about these single subject experimental designs. They are not very popular in general in psychology. There are certain fields in which they are popular. One of those is school psychology. Now, before I go on, I wanted to put in a little plug. I generally do this. What I usually do is I ask the class, is there anybody here who's interested in being a school psychologist or is thinking about that? What school psychologists do is they work in the school system, usually in a school district. So for most districts, unless they're really, really big, there would probably be only one school psychologist assigned. And they would do the sorts of things that the school district needs a psychologist to do. So you'd probably be giving IQ tests. And then your primary thing you'd be doing is working with kids who are having some sort of behavioral problems in class, typically. Now, what I tell people is I ask them how many people are interested in school psychology. I get one or two people raising their hand. And then I ask how many of you are interested in counseling and clinical psychology, and I'll get like 60 people raising their hand. Well, now, I don't know what your situation is if you're interested in going to clinical and counseling psychology, but those are very, very competitive fields. Usually only about 10% at most of people who apply to those fields are actually accepted into those fields. And so some of you may have great grades, you're going to have great GRE scores, you're going to have no problem getting into a clinical or counseling program. But I bet some of you are not in that situation, or maybe your grades and your GRE scores are not good enough to get into a clinical or counseling program. I think you ought to consider school psychology, because I think if you like working with little kids, you would be doing the same kind of things that you'd be doing as a counseling and clinical psychologist. But school psychology is a lot easier to get into graduate school. With just a master's degree, which is not in a program that's not too hard to get in, you could be working in the schools right after that. And if you want to go on to get a PhD, you even make more money. And school psychology has the most job opportunities of any field in psychology. There are more job openings for school psychologists than there are school psychologists. So you're almost guaranteed to get a job, and you can probably live wherever you want. You'll be very flexible. You could, if you have a spouse, say, whose job doesn't allow them to be flexible, you will be flexible if you're a school psychologist, so you could probably move anywhere and get a job. So I just want to put that plug in. If you're thinking about counseling or clinical psychology, maybe to think about school psychology. I have a cousin who's a counseling psychologist, and I asked him, I was at the family reunion over the summer in Colorado, and I asked him, I told him, I tell my students who are interested in counseling and clinical that they ought to consider school, and he was so enthusiastic. Yes, you should tell them that. So that's something that I want you to consider. Okay. Well, all right, so a little divergence. Now, getting back, so school psychology uses these two types of designs. We used to have a school psychology program in our department. We don't anymore. And when we did, it turns out school psychologists do one of two types of research. Some of them do correlational research, and then others do these single subject experimental designs. Well, we would not hire anybody who did single subject experimental designs when we had our program. And so let's talk about why that is and why these are controversial. These are going to be problems with all single subject experimental designs. So all three of the designs we talked about are going to have these problems. So there's 4 problems on our list here today. Underline this. Okay, first problem is likely type 1 and type 2 errors. Okay, because we can't do statistical tests and we have to analyze the data merely by inspection, what that means is we're very likely to think a treatment works when it doesn't. Remember, in the reversal design, we still have a 17% chance of making a type 1 error. And then we also have the possibility that we're going to miss a treatment that doesn't actually, that we're going to miss a treatment that would work, but we didn't have sufficient power to actually find it to work. And so, yes, there's a very good chance you're going to make a type 1 and a type 2 error if you use these designs, far greater than if you use a group design, where you can use a statistical test to determine the exact probability you made a type 1 and type 2 error. Second, placebo effects are likely. Remember, you're using the subject as their own control, essentially, so they're going to know when they're under the treatment and when they're not, and they may change their behavior just because of that. There's really no way around that if you're using a person as their own control. Another problem is experimenter bias is going to be more of a problem in these designs than in group designs. Let's say we had an unscrupulous researcher who had a new, say, method for keeping an autistic kid from hitting himself. He's going to use a reversal design. There's no rule in the reversal design about how long the different phases, the A phase and the B phase, have to be. You can make them as long as you want. And so an unscrupulous researcher might do the following. We're going to have the A phase where we're going to measure the kid without the treatment. And so some weeks the kid's going to be worse than others. He's going to hit himself more than others, some weeks more than others. And so if we're an unscrupulous researcher, we could wait for a week where he's hitting himself a lot and make that the A phase. So he's hitting himself a bunch. And then when we see that he's getting better, he's not hitting himself as much, boom! Then we introduce our treatment and we start the B phase. And now when he's in the B phase and he starts hitting himself a little more, now we're going to switch back to the A phase. And then when he's not hitting himself so much, we switch back to the B phase. And so because you have a lot of control as a researcher over when these treatments are introduced and when they're withdrawn, what that means is that if you want the research to come out in a particular way, you've got a lot more power to do that in a single subject experimental design than you do in a group design. And then the last thing, and this is probably what you may have thought about when we started talking about these things, is generalization difficulties. And what I mean by generalization difficulties is you're only testing one person in all these designs. You may find some sort of treatment that's effective for them, but it certainly doesn't follow that treatment's going to be effective for everyone because you're just testing one person. So since you didn't randomly select from the population here, you really aren't able to generalize to anybody else at all. Okay, for these reasons that I just listed, that is why these single subject experimental designs are not considered good for theory testing. You really can't use them to test theories very well. So, should these designs be published? Yes, they should be published. should they be published? Well, they should be published not because they're good at testing theories. They are not. They should be published because, for the second reason why it's good to do research. Remember the very first lecture? We said there are two reasons why you'd want to do research. One was theory testing, but the other is to solve a practical problem. And so the reason why these should be published is, let's say you're a school psychologist working with this kid, and you've tried a bunch of things and nothing is working. Well, what you can do is go into the literature, go into the journals that publish these single-subject experimental designs, and see, is there somebody else who has tried some treatment that appeared to work with this problem? Now, it's not very good evidence. These designs all have problems with them, as we discussed, but yes, if you are a working school psychologist, that may be a lifesaver for you. It might be able to give you new ideas that you can try with the kids you're working with. So that's why I think these are worthwhile, and that's why they should be published. Okay, that's all I had to say. Went a little bit over our 50 minutes, but we're going to have some lectures next week that are a little shorter. So no lecture on Friday. On Friday, starting at 12:01 a.m., you can start doing the stats quiz. And so you're going to do the stats quiz on Friday. Then you can either email your results to me, or you can send them through the mail. Remember, if you have questions, my email address is ecooper@istate.edu. Okay? So we'll have another lecture on Monday. Y'all have a great week.